Welcome to Goldwyn. Greetings, eager minds. You've just stepped into a realm of knowledge and discovery. At Goldwyn Edu, we're not just a channel, we're your partners in learning. In each video, we aim to ignite your curiosity about specific subject. From in-depth tutorials on mentioned key topics to thought-provoking discussions about another subject, we're here to make education not just informative, but exciting. Your voice matters in this classroom without borders. Engage in the comments, ask questions, and let's build a community of learners sharing their passion for knowledge. Never miss an enlightening moment. Hit that notification bell. We've lined up a series of mind-expanding content, and we want you to be at the forefront of this educational journey. Connect with us beyond the videos. Join us on mention other platforms for extra resources, live Q&A sessions, and a chance to dive deeper into the subjects you love. Educationally yours, Monowar Masud Goldwyn. Source of uncertainty due to pressure indicator calibration. Exploring uncertainty in pressure. Indicator. Calibration DKD-R 6.1. Guidelines. Greetings, fellow enthusiasts of precision. Today at Goldwyn, we're delving into the intricacies of pressure indicator calibration and the associated uncertainties, guided by the esteemed DKD-R 6.1 guidelines. Understanding DKD-R 6.1 guidelines. DKD, or Deutscher Kalibrierdienst in German, provides a comprehensive framework for calibration. We'll unravel the specifics of how DKD guidelines influence the calibration process and dissect the sources of uncertainty that emerge. Key discussion points. Join us as we navigate through critical aspects such as measurement uncertainty, etc., shedding light on how they contribute to the overall uncertainty in pressure measurements. Engage and learn. As always, your input is valued. Share your thoughts, experiences, and questions in the comments section. Let's build a knowledge-sharing community where we collectively deepen our understanding of this intricate calibration process. Stay tuned for insights. Hit that notification bell to stay updated on our journey through the world of precision calibration. We've got more informative content lined up, and you won't want to miss it. Educational exploration. This discussion isn't just about uncertainty, it's a learning journey. Grab your notepads, bring your curiosity, and let's navigate the realm of pressure indicator, calibration, uncertainties together. The center distance of two adjacent graduation lines, scale interval, is determined by the design of the instrument. The recommended ratios you mentioned, 1:2, 1:5, or 1:10, suggest that the width of the pointer is a fraction of the distance between two adjacent graduation lines on the scale. Here's how this ratio affects the resolution. Ratio of 1:2. This means that the pointer width is half the distance between two adjacent graduation lines. A ratio of 1:2 typically indicates a relatively high resolution, allowing for finer measurements. Ratio of 1:5. This suggests that the pointer width is 1/5 of the distance between two adjacent graduation lines. A ratio of 1:5 provides a moderate level of resolution, suitable for general-purpose pressure measurements. Ratio of 1:10. With a ratio of 1:10, the pointer width is 1/10 of the distance between two adjacent graduation lines. This ratio implies a higher level of precision, suitable for applications where very fine measurements are required. Resolution of digital pressure indicating device. In digital indicating devices for pressure measurement, the resolution is determined by the smallest change in pressure that can be displayed, often referred to as a digital step or the least significant bit, LSB. The resolution corresponds to the sensitivity of the device and is crucial for accurate pressure readings. The concept you mentioned, where the indication does not vary by more than one digital step when there is no load on the pressure gauge, suggests that the resolution is the smallest change in pressure that can be detected and displayed by the digital device. In other words, the device should be able to register and indicate a change in pressure as small as one digital step. For example, if you have a digital pressure gauge with a resolution of 0.1 psi, it means that the gauge can display changes in pressure as small as 0.1 psi. If the pressure reading is 100.0 psi and the gauge is sensitive to 0.1 psi increments, the next possible readings could be 100.1 psi, 100.2 psi, and so on. The resolution is typically specified in the device's technical specifications or user manual. It's important to consider the required level of precision for your application when selecting a digital pressure indicator. Keep in mind that the resolution of digital pressure indicators is often influenced by factors such as the sensor technology, the analog-to-digital converter (ADC) used, and the overall design of the device. Always refer to the manufacturer's specifications to determine the exact resolution of a particular digital pressure indicator model. Zero deviation, F0, understanding. Zero deviation, F0, in pressure gauge calibration. Zero deviation, denoted as F0, in the calibration of pressure gauges. Specifically, we'll focus on the critical process of setting the 0 point. Defining zero deviation. Zero deviation, or F0, represents the deviation of a pressure gauge reading when the instrument is completely relieved, typically at atmospheric pressure. This is a vital parameter ensuring accurate measurements across various pressure ranges. Setting the 0 point. Before each measurement cycle, which consists of both increasing and decreasing pressure series, the 0 point needs meticulous attention. It's crucial to set it at atmospheric pressure, ensuring the gauge is completely relieved. This process is repeated before and after each cycle. Recording the 0 point. Precision is key. The 0 point is not just set, but meticulously recorded before and after every measurement cycle. This meticulous record-keeping is fundamental for validating the reliability and accuracy of the pressure gauge. Instrument relief. To ensure an accurate reading, the gauge must be completely relieved during the 0 point setting. This practice minimizes any residual pressure effects, guaranteeing a true baseline for subsequent measurements. Cycle repeatability. The 0 point setting ritual isn't a one-time affair. It's a recurring process, emphasizing the importance of consistency and repeatability in calibration cycles. This meticulous approach ensures the gauge's reliability over time. Next. Steps. Ready to witness the zero deviation process in action? Stay tuned for our upcoming video where we'll dive deeper into the practical aspects of setting the 0 point in pressure gauge calibration. Repeatability, B, in pressure. Measurements. According to DKD-R 6:1, repeatability, B, is simply the consistency of an instrument's measurements when the mounting remains unchanged, calculated by comparing the differences in zero signal-corrected values across similar measurement series according to DKD-R 6:1. Repeatability, B, in the context of DKD-R 6:1, is essentially a measure of how reliably an instrument produces consistent measurements when the setup remains unchanged. This is determined by examining the variations in zero signal-corrected measurement values across corresponding measurement series. In simpler terms, it's about assessing how dependable and repeatable the instrument is in providing accurate readings under the same conditions. Reproducibility, B. The reproducibility with the instrument being mounted repeatedly and the conditions not being changed is determined from the difference of the zero signal-corrected measurement values of corresponding measurement series. Reproducibility, B, is the measure of an instrument's consistency when mounted repeatedly without changing conditions. It is calculated by examining the differences in zero signal-corrected measurement values across corresponding measurement series. In essence,
It gauges how reliably the instrument can produce consistent readings under repetitive mounting and unchanged conditions. Reproducibility, B, is the measure of how consistently an instrument delivers the same readings when mounted repeatedly without changing conditions. It is assessed by examining the differences in zero signal-corrected measurement values across corresponding measurement series. In simpler terms, it gauges the instrument's ability to provide reliable and consistent results under repeated mounting and unchanged conditions. Hysteresis H. In DKD-R 6:1, hysteresis H is calculated by finding the difference in zero-point corrected measurement values between the increasing and decreasing series when indicating mean values. Hysteresis H, as per DKD-R 6:1, is calculated by finding the difference in zero-point corrected measurement values between the increasing and decreasing series when indicating mean values. In simpler terms, it measures the variation in readings between ascending and descending series to account for any discrepancies in the instrument's response. The end. Thank you.